Well, hello and welcome to this A2EP webinar on solar heat for industrial processes, looking at the Australian opportunities. You may recall, for those that joined us at the recent Australian Renewable Heat Conference, we only very briefly touched on solar thermal projects due to the lack of projects happening locally in the last few years. But that does not mean solar thermal does not have a big role to play in decarbonising processor heating, as we've seen with the recent announcement for the Mars project in Wodonga. So it is time for us to look in more detail at the opportunity for solar thermal. My name is Jared Leake and I'm the CEO for the Australian Alliance for Energy Productivity, or A2EP is much easier. And we'd like to commence this webinar with an acknowledgement to the traditional custodians of country throughout Australia and their connections to land, sea and community, and paying our respects to their elders. This webinar is being brought to you by our beautiful broad cross-section of members here who all share our journey to improve energy productivity in Australia and to decarbonise our industries. And so we pay thanks to these fabulous members that give us the support and time to pursue such excellent topics as solar thermal. From the A2EP team today, I'm very thankful to be joined here by our membership manager, Mark Barber. Mark is going to be running proceedings today. And so with that, Mark, I'd like to hand over to you.
Thank you, Jared. Next slide, please, Jared. So we're very fortunate to have a lineup of great speakers. We've got Bärbel from Solrico, Keith Lovegrove from ITP Thermal, François-Xavier Sarda from newheat, Ken Guthrie from Sustainable Energy Transformation, and Paul Matuschka from Mars Pet Care. Our first speaker will be Bärbel. A little bit about Bärbel. Bärbel is a recognized renewable energy journalist and a physicist with almost 20 years of experience in researching, analyzing and writing in the renewable energy sector. She's MD for Solrico, which is an agency for solar market research and international communication, and founded by Bärbel in 2009. Solrico has teamed up with independent solar thermal experts in major international markets. The growing network has currently correspondents in Germany, Portugal, Bulgaria, Canada, Kenya, China, India, Italy, Spain, and Great Britain. So I'll hand you over now to Bärbel. Thank you.
Thank you, Mark. Great news to be with you today. Yeah, it's almost 30 years already. Time is flying for my being in the solar thermal sector. I would like to talk today about trends and innovations in the global solar industrial heat market. Well, let's go straight into it. We have good news from solar thermal, as we have a big variety of collectors covering different heat transfer media and different temperatures. So it starts from the lower part, where air collectors can be used until about 70 degree, and it goes to the concentrating ones where you have up to 400 degree, and we call them, dish or parabolic drafts or Fresnel collectors. These are the red ones here, where you can even do distilling, nitride melting, pulping, drying of paint. And in the middle, you have the stationary ones, which are flat plate collectors, either evacuated or not, or vacuum tubes, which go up to 130, 150 degree. We have developed a world map of turnkey solar process heat suppliers. This gives us a chance to send them questionnaires each year to find out about trends in the market. And this is where my presentation is based on. We have started these kind of surveys 2017. We have 68 turnkey ship project developers listed, none from Australia yet. That shows that there is still something to come up. But maybe this new Mars project and the big IRENA funding will do something good on that. We have painted here the world's largest solar heat plants, and you see that there is one Australian installation among them. This data arrives from the Solar Heat Worldwide publication, which is the biggest report on solar thermal news and data. We have this 36 megawatt Australian tomato farming plant, where a tower plant provides heat for the glass houses, for the heat, the water purification. It's a very fertile plant, and it goes along with the biggest plants, the 8 biggest plants worldwide. We have this, which was already mentioned, this Mars pet care plant. And if you compare now the size of the plant, we end here with 28 megawatt at the moment in Chile, which is a copper mine, flat plate collectors. And you will have one with 18 megawatt. So it already comes close to what we call the largest plants around the world, which is really good news. And I will hop over that as we have even somebody from Mars with us today, which is really great news. Yeah, so this is the development of the ship market over the years. We have now a tripling of the capacity installed worldwide, still on a lower level, but it's more than 1,200 systems that we have installed. The annual additions are marked here in orange and in gray. The gray bars in 2017 and 2019 have a special background. It was capacity additions in a big ship plant in Oman. Maybe I should say that we call SHIP solar industrial heat. So it's a short form for using all types of, solar industrial heat systems and technologies. And this ship plant in Oman was a rather large one. It was put up in phases, but then the project developer, which was Glasspoint at that time, bankrupt and the project stopped, even it was foreseen for a larger one. We have seen some increase in 2023 again after a little of a plateau in the Corona time. I think the project development times went longer in the Corona time, and so the dynamism has started now afterwards. This gives you some highlight figures of the ship market in 2023. We have already talked about the more than 1,200 systems. We have seen Spain, France, and China led the ship market in terms of new capacity. This is the green bar. This is mainly because of nice subsidies in Spain and France, and China in general has policies towards decarbonizing industry as well. What is an important trend, and I will come to this later, we have already 42% of the ship capacity worldwide newly installed in 2023 as concentrating collectors. This is an increasing trend. We see that solar heat is most popular among food, agricultural, and chemical businesses. These are the businesses which mostly use solar industrial heat systems at the moment. And we have the largest plant being built in 2023 was the Heineken brewery in Spain with 30 megawatt. Yeah, this is my first mega trend. Concentrating collectors are on the rise. What you see here in these pie charts is the new additions over the years and a forecast for the years 2024 to 2026 based on announced projects. And the red part of the pie chart is the concentrating collector area. So you see that we came from around 20% in recent years, and we will reach more than 70% in the coming up years. So the projects which are announced are rather in the field of concentrating higher temperatures. The biggest plant that was announced, not currently, already maybe a year ago, is from Glasspoint again, which was rebuilt in the USA. 1.5 gigawatt at the end, if it's once finalized, steam production for an aluminium refinery, first steam 2026, and based on Saudi Arabia's strong decarbonization targets. I will show you some installations of the year 2023 to give you some ideas on what is happening here in concentrating. This is, for example, a chemical producer in Belgium. They have built up a 3.9 megawatt parabolic draft collector field, reaching 20% solar share. The solar share here is a bit higher because of this big black box here, which is a high temperature storage, storing heat in cement rows, and that brings up the solar share. Actually, the project developer of this plant is the same one that got the turnkey contract for the Mars project. It's Aztec in Belgium. Another project in a completely different region, Mexico, is providing 160-degree steam for an ammonium nitrate producer. You see in a desert-like situation with very nice yields. Again, this time a heat purchase agreement with Heineken. Heineken has a strong, decarbonization target internally and is investing a lot next to their factories in decarbonization technologies, and often it's solar thermal. They provide 220-degree steam, and it's linear Fresnel collectors. They are a bit rarer at the moment than parabolics, which are the round ones, which will be also installed at the Mars factory. But we have a provider in Spain who did this plant. And we see a lot of novelties in this field. The number of parabolic draft manufacturers, particularly in our world map setting, is increasing. And this is one of the newcomers from Austria. And I wanted to share this with you. It's a completely different setting. Normally, you have the parabolics, which are stiff, you know, on a mirror, a bended metal or a glass mirror. And here, everything is made from foil. It's delivered in a container, as you can see here, rolled up, and it's then the metal rings are put up along it's a 200-meter row, and it's blown up. And the foil in the middle, the glass foil, the concentrating foil is also made from polymers. A completely new setting, and we are looking. They have now the second plant. It's a startup, so we will see how costs develop. And the second mega trend, which is, I mentioned this already, it's the heat delivery contracts will dominate the future of ship. Again, the same row of pie charts as before. We have here the share of heat delivery contracts against EPC contracts in the long run. And you see in the outlook 2024, 2026, the number of ESCO projects, also we call it ESCO, you know, like energy service contracts, is growing a lot. And we will have François-Xavier with us. They are specialized on that from newheat, so I will not go further into that. But the Mars project is an EPC one. That's what I was told. Yeah, I was asked to talk a bit about the enablers of the ship market growth. I think we have seen very good results from financing visibility studies in Austria in the last 2 years. I would like to know whether IRENA in Australia is also paying visibility studies as a preparation phase. I'm not sure about that. Investment grant subsidies obviously drive markets. We have these kind of subsidies in Germany, Netherlands, Belgium, France, and Spain, and they usually produce also larger plants that we have seen in the statistics in the last years. We have cost-effective solution markets with high fossil fuel prices, mainly oil in Mexico. Mexico is one of the strongest ship markets that we have worldwide. And we have the individual carbon reduction targets of multinational corporations, as I have talked about with Heineken. Yeah, so this brings me already to my summary. You know, I think that it's very important to stress that solar industrial heat is a proven and mature technology. We have a growing number of very committed project developers and experienced ones with improved business models. As I've said, you know, high temperature solar industrial heat solutions are on the rise with strong cost reduction potentials because it's still rather new, and they have now starting, you know, the roll up of their technologies. The increase of international corporations is a good sign, and we will probably see more companies that decide to do several, you know, of solar thermal plants for their factories as a whole. Then it's important to stress that we have solar thermal generally has attractive installation area requirements, as you need 3 times less area than PV for the same amount of energy. And solar thermal is always a good player for multi-source energy systems, which become more and more important to increase renewable shares in on-site production. So this is it already from my side. Thanks for the attention, and I'm looking forward to the Q&A later on.
Wonderful. Thank you, Bärbel. Mentioned there about IRENA doing the studies. Yes, they do. They co-fund studies. I think it's
Okay.
about 250,000 Australian dollars is where they start. But absolutely that is available to help with kicking off
Very good.
projects. Co-funding only, which can be a bit of a hurdle, but it is there available, which is great.
Good.
Good.
Super.
Mark, I'll get you to unmute and introduce our next speaker, and we'll be saving
Nice.
some questions up.
Yeah, thank you, Bärbel. That was such an inspiring presentation and such an impressive portfolio of projects. And a reminder to everybody watching that these slides will be distributed afterwards. So never fear, that you'll be able to go through those in detail. Our next speaker is Keith Lovegrove. Dr. Keith Lovegrove, to be precise, is the Managing Director of ITP Thermal. He's got 30 years experience in renewable energy combined with 15 years of teaching experience in undergraduate and postgraduate courses in energy systems and systems engineering. Keith has authored and co-authored more than 160 publications, including 2 patents and 7 book chapters and major public reports. Keith is currently a member of the University of Adelaide Centre for Energy Technology Advisory Board, serves on the Australian Renewable Energy Agency's Project Assessment Panel, is a board member of the Australian Solar Thermal Energy Association, and is chair of the steering committee of the Australian Solar Thermal Research Institute. Over to you, Keith.
Thanks, Mark. Are my slides clear okay?
Yes.
On the screen? Okay. Yes, so solar thermal. Thought I'd begin with a little bit of context for Australia. And this is a very similar picture to what you'll find in basically any industrialized country these days. So if we look at total final energy consumption, it's about 47% is our industry, and of that 52% is for heat. And of that, at the moment, 53% is natural gas. But we still have black coal being used for process heat in Australia. Now that we're talking about solar thermal, it's very important to consider the temperature breakdown of the usage. And you can see there that there's quite a lot in that 150 to 250 degrees band. There's also an awful lot in this greater than 600 degrees, and that can be just from calcining and iron and steel and very high temperature processes like that. So looking at the different sectors that are dominant, we've got the alumina sector as a very big user of heat, and theirs is split in sort of 50-50, and some very high temperature calcination, probably hard to abate kind of process, if you will, and a lower temperature digestion thing. We've got oil and gas, significant there, but in a decarbonising world, you might say, well, where does oil and gas go? Food and beverage is very important. That's dragged up in that analysis by our inclusion of sugar refineries, which are already using a lot of bagasse waste. So when you take them out, it drops down a bit. Iron and steel is an interesting one. And we've got the whole discussion of Australia as a potential exporter of green iron into the future, but that's a very long range story. And then other sectors going on down there with different temperature splits. We do need to think about the economics, and in that regard, we need to think about, well, what are these industry players paying at the moment? And if you look at the yellow bar in the middle, that's to represent natural gas prices. What we see is very large users. First of all, I'll point out that the horizontal axis there is a logarithmic scale of terajoules per year of consumption. And to put that in context, the 1,000 terajoules per year would be like a 40 megawatt thermal use at 80% capacity factor. So 100 is 4 megawatts, 10,000 is 400 megawatts. So very large users, the very, very large 100 megawatt alumina refineries and so on, are effectively paying the wholesale price of gas, which is, let's say, according to that graph, between $10 and $15 a gigajoule, very uncertain. But then the y-axis there is levelized cost of heat. So that's factoring in an approximately 80% conversion efficiency from the gas to the heat, which is why the wholesale price doesn't match the levelized cost of heat. It's rather higher. But what you see is, as you come down to smaller users, they pay more and more. They have to pay distribution and retail costs that the very large users don't. So you kind of get that sort of power law dependence. Now, there is some large users still using coal. That's, of course, cheaper. There's some users who are not connected to the gas network who actually have to truck in LPG and LNG. They tend to be smaller, hence those there. So that's what we're competing against. With solar thermal, Bärbel's already introduced the collector types, but we've got this progression from at one extreme, unglazed flat plate, which is your swimming pool heater on your roof at home, just to sort of warm things up to 60 degrees maybe on a good day. And what we're trying to show here is that as you go from left to right on that graph, you're facing increasing complexity in technology in order to get higher temperatures. So you've got the unglazed flat plate, then our glazed flat plate, the old solar heart systems, but on a more industrial scale, the evacuated tubes, adding a non-tracking mirror, then you've got the troughs or the Fresnel, and finally you've got central receivers or dishes which have the ability to melt ceramic bricks if you really want to. So you can sort of see how that complexity is going to translate to higher capital costs per kilowatt as you seek higher temperatures. So the graph is showing that as linear, but let me just say that's a rule of thumb. It's not exactly linear in a sense. This is a way of thinking about it. But then overlaid on that, what we've got is that this technology, as many other things, has an economy of scale. The bigger systems are more cost effective than little systems. So you've got this capital cost depending on both temperature and size. If we then translate that and look at that, how does that compare with what we're paying for heat from gas or coal or LNG at the moment? We turn our capital costs for the solar thermal technologies into levelized cost of heat. What you can see is you've got this power law effect, the cost effectiveness playing out, that the bigger systems are more cost effective. And interestingly, that whilst it is sort of analogous to the size dependence of the cost of gas, it actually comes down faster. So on the whole, the bigger systems are more competitive than the smaller systems. There's one factor, but then you also see the temperature dependence playing out. And what we see is up to 100 degrees C, more or less, it looks very competitive at all sizes and even competitive against coal. In the 200 and 400 degree bands, there's very good prospects compared to natural gas for users above 100 terajoules per year. At the 600 degrees, with the tower systems and so on, that's still a bit of a stretch, although it's almost touching some competitiveness under certain circumstances. We need to think about where our users are. So the map there tries to show different industry sectors, different sizes, different locations. You see quite a bit around our sort of seaboard, capital cities and so forth. The map on the left is direct beam radiation resources. That's what concentrators care about, the direct radiation, but the map of diffuse radiation looks very, very similar. So what you see is around the East Coast, near the coast, let me flip it around. If you go inland and you cross the Great Dividing Range, the solar resources pick up. If I just do this sort of 1800 kilowatt hour meter squared per year contour on our map, what you can see there is that's sort of the limit for where concentrators kind of make sense. So there's no absolute limit with that. But what you see is there's an awful lot of our country that looks very good for solar thermal, and it's probably not the best choice for Tasmania. But at the 100 degree systems, they look so competitive that we might do them in a much wider array of locations as well. So I thought I'd show a few case studies as well. This one in the winery in Griffith is a really classic one because it's only 200 kilowatts thermal. It's 95 degrees C, and I think really we should seriously look around at the country at a lot more of that sort of installation. There should be a lot of opportunity for that sort of thing. Bärbel already showed this, and it's worth showing just because of its scale, and it's interesting. And what I'd like to point out with this one, make the additional point that this is a combined heat and power system. So you've got a tower system there, which is capable of, huge temperatures which you don't need because fundamentally they're trying to do desalination and keep a greenhouse warm. But what they're doing is they're using the high temperature steam to do some power generation in a back pressure turbine, then getting the process heat. And that's a very interesting configuration to think about and has its own favorable economics. I would say, though, that combined heat and power system, the electrical turbine is very much undersized for a 30 megawatt thermal array, but that's just the business decision they made for that plant. I thought I'd show this one as well. It's not Australian, but just because it's so big, and just to sort of point out that people have already built solar industrial heat systems on this, on a scale that's already big enough for alumina refineries and the really big end of town. It's worth knowing that. My version of Mars Wodonga, which Paul will talk about in a minute, it's very good news indeed for actually the industry globally, but certainly in Australia, to see this progress. And I happened to see, Paul, Dominic Zahl showed me this morning, he's got a live, well, there's a live cameras on the site, and they've already started site work. So that's very impressive. You know, a project's real or realer when the site works have actually begun. So I was very impressed with that. So that my conclusions: decarbonising process heat is a major challenge. I mean, we all know that. There's a lot of talk about electricity, and the word electricity gets muddled up with energy in some discussions, but end use energy is only 20% electricity and it's 30% heat, and we really have to think about it. The smaller sites are paying more for their fossil energy. Solar thermal heat is cheaper for large sizes. Solar thermal costs more for higher temperatures. This leads to the economics look pretty encouraging in the 150 to 400 degrees C range, and below as well. Probably avoid our coastal fringes for concentrator systems. No reason that you have to, but the economics won't be as good. And as we've already seen, there's proven systems around the world. This is not new technology. Thank you.
Brilliant. Thank you so much there, Keith. And we've got Paul Matuschka online. I'll ask him to come off on mute and have a few words about the new project in a moment. But Keith, very happy to see that you're doing an update on the heat assessment there for Australia. You did that fabulous job in 2019 with ISF and BZE and Pitt and Sherry and the like. We've used that document so many times, that donut graph that you made, fabulous. So really excited to see a new version of that one coming, that's for sure. Good.
Yeah, thanks, Jared. Yep.
And then to Paul, yeah, congratulations on getting this project ahead, and great to see that ARENA on board and supporting you. Paul, Keith just mentioned that you've already started a bit of groundworks there. What's the time frame for the project?
Yeah, thanks, Jared. And probably just want to acknowledge first that thank you to A2EP that supported us to, with ARENA's backing, I guess, into when we did a pre-feasibility study into this back in late 2019, early 2020. So that is definitely very important work to help supporting in some of these projects, and this is a result of that collaboration at that start. So yeah, where we're up to is obviously Mars in this release, and obviously the Prime Minister's there, and Keith's slide announced on the 29th of October that Mars Wodonga, Pet Nutrition Australia, for our Wodonga manufacturing facility, has a 100% renewable energy solution. One of those projects is concentrated solar thermal, which is co-funded by ARENA. Yep, the civil works has commenced, and Keith, yeah, I shared that website with the global team yesterday and copied Dominic on it, so it's probably front of mind. Civil works has started. We expect to be mobilising and installing solar collectors around about January, February next year. Commissioning at this stage should be January, February 2026, and we should be operational around quarter to 2026.
And Paul, your operating envelope there, are you needing the steam 24/7 because that steam accumulator capacity, is that going to be enough for you? What's the plan to balance the load when the steam's available and storage and things?
Yeah, so our portfolio of solutions to reach 100% renewable is, and there's this whole dynamics about how you reach 100% solution and what's the right pathway for us. And we've done a lot of work, which I'm happy to talk through in more detail, I guess, with people that are interested in that at a later stage. But predominantly, we are targeting 50% displacement of our natural gas with concentrated solar thermal, with the thermal energy storage and steam accumulators that we're putting in to the plant. And that's to buffer out our operational demand against our summer winter generation profiles. We're also looking to do the next stage of the graphite energy ETES solution, which would do around about another 25 to 30% of our steam demand. And then the last 20% is with renewable gas guarantee of origin through the Murray Valley hydrolyzer plant. So that renewable fuel offsets, and the intent is that all the three steam generations, so the combustion renewable fuel system, which will be about 20%, will still operate. The heat to heat solution, concentrated solar thermal, will operate, and the power to heat solution will operate. And those things combined and all the steam processes integrated together will give us that 100% solution. And utilizing, obviously, then you utilize the last 20%, which is a challenge from a storage perspective. Tapping into storage within networks and power from energy and that sort of thing.
Thanks for that, Paul. I mean, we often hear about this idea that there's no silver bullet to solve all these problems. I think you've just summed it up so well there, having to look at utilizing these 2 or 3 technologies to get you through. Thanks for that, Paul. Look, we might keep going with our next speaker, and Paul, just staying on. So if we've got some questions there, they may well come through, and we'll get to you at the end. But I'll hand back to Mark for an intro of our third speaker.
Yeah, thank you, thank you, Jared, and thank you, Paul. And just a reminder to everybody, please feel free to post questions in the Q&A. So the panel's waiting afterwards will be waiting afterwards to answer any questions that pop up during these presentations. Introducing François-Xavier Sarda is Business Development Manager for newheat. newheat is a renewable heat supplier for large energy users. And they provide a heat as a service business model, and they help clients reduce Scope 1 emissions and lower energy bills. Over the past 7 years, François has driven to newheat's growth by developing projects in Europe and Australia. Over to you, François.
Thank you, Mark, for the intro. And thanks, A2EP, for allowing me to be here and present a bit of our experience in solar thermal. As Mark mentioned, I'm François-Xavier Sarda. I'm business manager for industry for newheat, and I have a special connection with Australia as I've been in Sydney for the last 2 years. I just recently came back to France, but I've been busy developing our project there. Just a quick word about newheat before starting talking more specifically about solar thermal. We are a heat as a service provider. We develop, design, build, and operate large renewable heat assets. And we combine different technologies, as you can see on the right part, starting from heat recovery to solar thermal, geothermy, electrification, and combining that with thermal storage. And solar thermal has a very special place for us. This is where newheat started, and this is the technologies we've been using for our first project. We are based in France, by the way, in Europe. Today, I wanted to share with you 2 case studies. One of our solar thermal project in France for a dairy factory, And one case study for a project we were studying in Australia recently in New South Wales. But before diving into the case study, I wanted just to take a large view of solar thermal and from our perspective, how does solar thermal works and where does it make sense? And very simple slide here, but very important from our point of view of heat provider. These are the four factors, key factors that impact the economics of a solar thermal project. Of course, first and an obvious one is the sun radiation. The more sun you have, the better the system will work and the more energy you will harness from the sun. Then we had the previous panelists talking about that, but the target temperature, and I think the graph Keith shows us was quite obvious, and that is how temperature impacts the efficiency of solar thermal systems, whatever technologies are used. And the lower temperature we work, the more effective the systems are and the more efficient, and at the end, the more economics beneficial the system can be. Then Keith also mentioned that, but the scale of the project, the larger we can reach better economy of scale and the economics gets better. And then of course the last wheel is financial incentives when needed, and what Arena is doing in Australia is quite inspiring as well. We have strong support in Europe and in Australia as well and other parts in the world, but they are helping to align economics of the project with current fossil fuel price. But that being said, if you take these all four parameters, you can play with them. And if you are in a place with a lot of sun radiation and low temperature process, you can imagine having a competitive project with smaller scale and with lower incentives. And that's playing like that, pulling the trigger of this project. All right. I'll start with presenting you a project we commissioned with newheat last year in 2023 for a dairy spray dryer facility. It's from Lactalis Group. You may have heard of. Lactalis has some plants in Australia as well. The solar thermal plants, we're using flat plate here, targeting, as I mentioned, lower temperature to gain efficiency in a place where there is not so much sun. It's a 12 megawatt system, around 15,000 square meter collectors. And this is a project where newheat plays a role of heat as a service provider, but also developer, builder, and operator of the system. We will look for that on the next slide, but this is a system where the solar heat is used as a preheater of fresh air. The plant itself is using air to dry some milk, to transform milk into powder, and the drying process occurs at about 200 degrees. However, they are using fresh air, which is heated up to 200 degrees, and the fraction from ambient temperature to 100 degrees is at lower temperature, and this is where we are integrating the solar thermal heat, the solar heat. Here's a more schematic diagram that might be easier to read there. So you have the solar thermal plants, 15,000 square meters, I mentioned. We have a big buffer tank. It's basically a big hot water tank, 3,000 cubic meter, which is very well insulated and very well certified to make sure higher temperature on the top, lower temperature on the bottom. And then through some air to some water to air heat exchanger, we preheat the fresh air before it's heated up by the existing installation of the factory. So it was an existing process where they have gas burner and steam heat exchanger, and what we've done is adding an additional water to air heat exchanger to preheat the fresh air. Well, the sky view of the project where you can see the solar thermal field on the back. This big storage, which is between solar and the factory and the factory itself with the spray dryer inside the tower. Some specificity about the project, it was kind of a challenge to, even we are very close, and we've been lucky enough to find some land close by, which was not belonging to the site, but we found it ourselves. You may see there is a railway between sites and the solar thermal field. It's a small one, but it's still a railway, and it was kind of a challenge to manage to cross it with hot water pipes. Not so much technical challenge, but more on the approval with the competent authorities. It took us a bit of time, and just saying developing solar thermal project is a long journey and not an easy one. It takes time and resiliency. I think Paul mentioned first studies for the Mars project was done in 2019 or 2020, if I heard well. Well, that's typical time frame for solar thermal project. Few years of development to align the finance, the approvals, technical studies, and also on. And the quick zoom before I move on to the next case study, but quick zoom on the heat exchanger I mentioned to you before. So it is water to air heat exchanger that we install inside the process. And I didn't want to talk more about heat exchanger, but more about process integration. Temperature is so important for solar thermal, but also for other technologies such as heat pumps, where we have the same issue of having better efficiency at lower temperature. And on existing industrial sites, most of the time, they've been built around steam network. The easy way and the most logical one, they design the system to match with the highest temperature needed inside the process. But when we want to decarbonize this process, we really need to go inside the process to target the lowest temperature possible first, which is where we can be competitive and decarbonize without compromising with energy prices. And this is something we do for each of our projects. It's really rare now for us to integrate into utilities scale. We really need each time to go inside the process to reach to match the perfect temperature to make the system works better and more efficiently. I won't spend much time on this, but this was just how the project was financed, and just to illustrate the heat as a service approach we have here. Instead of selling to Lactalis to the sites solar thermal plants, which was not an option for the site because of the higher capex, what we've done is financing ourselves the project through a special purpose vehicle, and we set up a heat purchase agreement for the next 20 years. So we will be selling the heat to Lactalis. They committed to utilize this heat, and on our side, we are committing to produce the heat. We have efficiency threshold, and this will go on for a long time. This, from our perspective, this is a very interesting business model when the industrial side does not have the capacity, the capex capacity, or doesn't want to invest into energy systems, preferring investing into its own process and into expanding the site. I'll quickly run through a case study we had in Australia. This is for a meat industry in New South Wales. Very specific one, but very interesting as well, where this was a site where steam is used as a main energy vector. But when we've been on site, we realized only one very small processes really needed steam. All the other processes were using heat below 100 degrees. And the studies we've done there and the proposal we've done there was to switch everything from steam to hot water, and then to integrate a combination of solar thermal and heat pumps. Just focus on the graph on the left, where you can see solar thermal. The blue line is the total consumption of the site, and the orange bar is the production of solar thermal. So we can clearly see in the summer season, solar thermal provide about 100% of the demand, and you have a small gap in the winter season, where our proposal was to combine solar thermal with heat pumps to fill the gap and to reach 100% decarbonizing heat supply. What I wanted to show you for this case study, besides of the technical find, was more on the economic balance for the sites. Well, we had to get everything anonymous, but the idea is still there. On the gray line, we have the gas price projection for the site, growing of about 3% per year. That's the assumption we took at this time. And the orange line is the heat price, the solar thermal price. As you can see at year 1, so the number here 1, 2, 3 until 20 are the year of the project, and at year 1, solar thermal is slightly below gas price. But one of the key and very strong force of solar thermal is its stability and independency. So it's not moving. It's slowly rising because of inflation, but otherwise it's staying the same for 20 years. And as the gas price is moving, so on this forecast, we put a very stable and slow increase, but it can usually go up and down and up and down. But solar thermal is not moving, staying the same, providing stability and independence. And well, very few savings the first year, but as you go on and gas price is rising, solar thermal not moving, we can see the savings from the site on its energy bill is increasing over time. And at the end, it's really not ridiculous, and it's pretty high. We were talking about 8 to 10 million Australian dollars saving over 20 years for the site. I've been very quick on this slide, but that's time for my conclusion. It's going to be very brief as well, but from our perspective, solar thermal is a key technology for heat decarbonization. Its main forces are providing stability and independence from the grid. It's not connected to gas price, to electricity prices. And we hope we'll see more of these projects in Australia. Very happy to see the Mars project moving here, and hopefully we'll see more of this in the future.
Brilliant. Thank you so much for that, Francois. And this really highlights that opportunity. And I like the milk dryer one's got to open your mind up to say, we don't need to replace the entire amount of fossil fuel steam production or for hot air for the dryer straight away. Hey, what can we do with solar thermal here and now and at least do part of it? So that's a great reminder. We don't need to do this all in one step as well. So thank you. Absolutely great. We're about to go to a panel discussion, and I'll have Mark introduce our final panel member in a moment. But before we do, I just wanted to share some news. Bärbel mentioned before, said, do we have any sort of local champions in Australia for solar thermal? And the answer is yes. We have Impacts Group, and I think Peter Blackmore is on the call today. We might be able to bring him out of the audience to chat on this if need be. Amazing announcement just came out recently that Impacts has been awarded a grant and is going to be part of the Charles Sturt University Agricultural Centre of Excellence, where they're going to actually install the demonstration plant for solar thermal there alongside some other technology. So this is a fabulous step forward, and their technology looks fabulous as well. Looks like it solves a lot of issues of installation cost and time, and even materials as well. So Peter, can't wait for that one to come into a demonstration and see much more from Impacts going forward. So I just thought it'd be worth bringing that one up. But now I'll just go back to Mark. Mark, are you there to introduce, because we haven't introduced Ken Guthrie yet?
Yes, we can't forget Ken. Ken Guthrie Ken Guthrie AM is the Director of Sustainable Energy Transformation Proprietary Limited, a specialist consulting service that undertakes activities that aim to transform markets to support greater use of sustainable energy. Ken is the Australian Executive Committee member of the International Energy Agency's Solar Heating and Cooling Program, representing the Australian PV Institute, of which he is a board member. From 2014 to 2018, Ken was chair of the IEA Solar Heating SHC program, and until the end of 2017 was the chairman of the ISO Standards Committee on Solar Energy. So it's great to have you on the panel, Ken. So now we move to a phase of taking questions.
Fantastic. And before we do that, Ken, any observations, comments on the presentations that we've had thus far? Maybe you knew all that already.
Yeah, well, no. Look, I think it was really, it's been a great roundup of things that have been said. And I'd particularly like to emphasize the point that François-Xavier made about integration being a key component. It's not just about getting the technology there, it's about making sure you put it in at the right spot. There's some work done on the International Energy Agency solar heating cooling program, task 49 a few years back, on looking at integrating solar heat into industrial processes. So that'd be something worthwhile having a look at if anybody's keen to find a bit more detail on that. But yeah, solar heat's got a lot to offer for industrial processes. It's with the instability in gas prices and gas availability, it provides something where you pay for it up front and you got certainty for the next 20 years, which is something that's really valuable in the current business conditions. And also it doesn't require any or very few critical materials that you might be required with other sort of technologies as well. So there's lots of opportunities there, but I think we've had a great roundup of what's happening, and thanks very much for putting it on.
Excellent. Thanks for those comments there, Ken. Why don't we go through the questions? I see a first one here from Raj saying at which stage does the phase change from high pressure hot water to steam vapor occur in the parabolic and concentrating collectors? Does it need a flash vessel and or MVR? Who's best for that one? It might be one for Francois.
Or maybe I leave it to Keith. That might be more
Oh, look out, I'm bouncing around.
more
Go, Keith.
precise on myself on the technical aspect.
Wins.
I'll certainly have a go. And Paul might want to come in here as well. Arrays like that proposed for Mars are producing saturated steam. So there is a phase change going on progressively, but there's no dry out region in the trough receivers, as I understand it. And then there would be separation in the storage vessels. There has been some demonstration projects in trough receivers taking them all the way to superheated steam. But the separation issue has to be managed carefully because you get very fast, sudden changes in heat transfer coefficient. But let's say if it's saturated steam, it's no issue. It's just happening progressively. For higher temperatures, the trough plants that are used in concentrating solar power plants, they actually use oil as a heat transfer fluid, and then they run that into a boiler heat exchanger where there is a separation vessel.
Gotcha. Thank you for that, Keith. Paul, is that lined up with your plans as well? Just saturated steam out of the collectors and then a bit of separation in some vessels afterwards?
Yeah, Jared, and I am not the technical person to answer that question. That's why we've got Fichtner and Vast and Gasco and Rawtech and people like those working on our system.
Gotcha. And finish that one off, MVR, Raj. I'm not aware of MVRs being used at the moment in conjunction with solar thermal, but maybe that's because Raj hadn't mentioned it before, and so now someone's got to go back to the drawing board and have a look at this to see if we can do low temperature steam and then pump it up with MVR. But thanks, Raj. More homework
Nice idea.
there. Yeah.
The next question on the list of questions is actually looks like it's from you, Bärbel. Would you like to verbalize that question regarding?
I was asking for the storage. I talked yesterday to Artstech, and they confirmed that they do direct steam production within the receivers, which is really a novelty, because as we said before, the systems that I showed you from Artstech all produce like oil first and then produce steam outside the collector field. So that's that they will run it on water and do direct steam production in the field. But they explained me as well that Mars did separate tenders for the different components of the field. So it seems that there is another tender taking place for the storages. And I was interested who is responsible for the storages, because Aztec will only provide the collector field, the parabolics and the hydraulics around it.
Correct.
Paul, do you know on that?
Yeah, correct.
Well-
So we are contracting with Levo to supply the steam accumulation tanks. But then the balance of plant, which is being contracted out, we're getting support from Gasco in Australia in that space for the integration and operation from the solar collector field into the steam drum and steam accumulators and so forth, and then integration back into the plant. And
okay,
yeah. And I agree with Ken's comment and Francois' comment that integration is a primary consideration in this project. Obviously, in our ETES installation that we've already done, we've put a lot of effort into getting the integration right into one plant, and obviously moving forward with concentrated solar thermal, we'll have a combustion boiler and ETES steam generation system, all producing steam at different times, and they'll be integrated together. So there's a lot of effort going into the design, which also is work in progress of the final operation and how we control all these systems together.
So you're going to be needing to coordinate 3 systems here eventually, Paul, between the existing boilers, the ETES, and the solar thermal, yeah?
Correct, yeah.
Okay. We'll be looking
May
forward to
I
sharing
ask
the IP
here?
on that one.
I would like to know at this point, why did you decide against ESCO? I think Mars decided to operate the systems at the long run and do EPC contracts. Why did you decide that?
Versus a heat purchase agreement?
Exactly, yes.
Mostly around I guess the easiest answer is that there's none of this installation in Australia. So the difference between that and a solar PV installation, it's common in place. All the learnings have been done. You can go to market and get a power purchase agreement where where it's competitive. In this installation, as Francois said, it's been a 5-year journey to get to the point of announcement for the project, let alone another 14, 15 months for building it. We couldn't find a cost competitive heat purchase agreement to compete in that space. So we're getting co-funding from ARENA. It's just the whole complexities in that space about being a first mover in this space, that a capital purchase was obviously still go through lots of hurdles and justifications and all that sort of stuff, but a very much in inverted commas an easier process than trying to find a competitive heat purchase agreement. Now that's not saying that won't be the case into the future, and that we expect that within Mars once these systems are deployed and we see that the operation of them in Australia and in a food manufacturing sense, that they will become competitive, and that's part of obviously the glide path with ARENA and so forth. But that's probably the answer.
Thanks,
Thanks.
Paul. Mark, I
Jared,
think we might take
Jared,
the
I'm
next 2 together. These next 2 questions, I will look in the chat. We've got one from GU and Anthony Kimpton from Tony there. This is almost a combined one. I'm going to be calling on Keith here for this one. And we're talking about comparing solar thermal for hot water production versus a heat pump. Let's say if we've got a heat pump of a COP of about 3, and so which is the which one is likely to be the more economical here? Keith, I saw from your graph that around 100 degrees, obviously it's coming down a lot, very steep in terms of the dollars per gigajoule levelized cost of heating, that is, levelized cost of heating, LCOH, which combines OPEX and CAPEX so that we can have a fair comparison between technologies. You're showing in a decent size below 100 degrees down sort of $5 to $10 a gigajoule levelized cost of heating. And I suggest that's pretty similar for a COP of 3 and a heat pump as well is going to be in that in a typical situation where you're getting $100, $120 per megawatt hour. Keith, what's your take on these different technology options?
Yes, in that 2019 report that you referenced earlier, which is still available publicly, we've done analysis on lots of different scenarios of different technologies, and I'd say at the low temperature end, there's no clear winner. So if someone's looking for that low temperature heat, they should look at both solutions really carefully. It's site dependent, solar resource dependent. But the low temperature 100-degree systems in solar thermal still look very competitive against heat pumps. Now with heat pumps, the COP is going to drop as you go to higher temperatures. So there'll be a maxing out. And once you're into this sort of saturated steam territory, well, the concentrators are then more expensive than the flat plates, but still the heat pumps it's a territory they can't really go to. So that becomes the choice then. There is of course the MVR technology, which is interesting, and how that, for people who don't know, that's mechanical vapor recompression, where if you've got some low temperature steam, you just run it through a turbine and hey presto, you've got high pressure, higher temperature steam. The critical thing there is you already have steam, so you don't have to do the phase change. So anyway, the answer is no simple answer. You have to do careful analysis site by site,
Absolutely.
application by application.
If I add to that, things like having to upgrade the electrical connection, that might see the heat pump fall over. If you can integrate the heat pump with an existing refrigeration plant and get that benefit, that might improve things. Ken, what do you see as those sort of decision criteria there, and for which benefit, which way to go?
Look, I agree with Keith. When you're in the lower temperature area, there's depends on the particular situation. But there is another technology that's sort of becoming more used around the world called PV2, or photovoltaic thermal, where you have you collect the heat off the back of a photovoltaic. You can put that the electricity into a heat pump, and you can use the heat to preheat the heat pump and cool the PV. So you end up with getting more value out of it, both as far as heat and electricity is concerned. So that's a good option. There are a couple of manufacturers of PVT in Australia that are just starting up at the moment, and there's a number of them internationally around.
Absolutely.
So that's one of the possibilities. The other thing is, if you don't go for a heat pump, if you've got a solar heating system, your pumping power is of the order of 1 to 2%. So you've got a COP of about 50 to 100. So that means you're using less electricity to do that work, and the electricity price is the thing that, of course, is going to vary in future.
Jared, I'm wondering if at this point, I see that we've got Peter Blackmore in the room. Maybe we could bring him online to make some more comments about his announcement. Let's
do that. Give me a second there to bring him online. Would you want to go to the next question? I'll get Peter up.
Yep. So a question from Glenn Ryan. What is the panel's view on the opportunity for solar hybrid PVT in Australia?
There we go. I think that thanks for that, Ken, getting ahead of the curve. That's great, perfect. Yeah. So Glenn from is it Son of Eight doing the PVT with collecting it to air, and Cool Sheet in Australia, in Sydney here, collecting it for hot water, doing a project at North Sydney Aquatic Centre. So yeah, good options there. Peter Blackmore, we've got here from Impacts. Peter, congratulations first of all on your project there for Charles Sturt. Peter, any further comments on this, on the costs for hot water production, solar PV versus other?
Yes, well, that's been a bit of a contentious area for us, but so our panel is designed for the higher temperatures. Well, we'll be going up to the higher temperatures, so up to 400, 450. And for those who don't know, this is a flat panel, about 60 mil high, 2 by 1 meters, and it's a virtual parabola. Done with a coating via University of South Australia, and with a 30-year life, totally recyclable at the end of all of that. So it's going to have a much lower building cost because you have the concomitant reduction of frames and mountings and all those sort of things. Although we do have a fairly accurate slewing motor to keep that facing the sun at all times. So yeah, we're pretty excited about this. When CSU were having internal discussions about looking at some of the challenges before it actually went official, the professor in charge of the vineyard of the future in the winery said, "I'll take the heat." So that's going to be the first stage, and then later we'll add steam, and then we'll go to a turbine and do a cogen. So yeah, that's all going to be pretty exciting for them and for us. So we're hoping to have the first 2-module demonstrator up at the beginning of July, and that's 8 meters long. Two modules, 8 meters long. They'll be about 4.5 high when it's in the morning or the evening position.
Fabulous, Peter. I hope you're up for the challenge there. Keith showed that range of existing natural gas boilers and delivery of heats, often around that $15 to $20 a gigajoule there. And yes, we've got support from ARENA with their ITS funding and what have you. But really it has to stand on its own 2 legs eventually. So Peter, I hope you're focusing in on that one and look forward to delivering that steam in
Our
that range.
CFO has done quite a bit of work on this, and he thinks our LCOE is 850 to 950, and that's as made out in that graph before. That's flat for the 20 years or 30 years.
Yeah, wow.
So,
Bärbel, what sort of, any commentary on what you're seeing, that sort of levelized cost of heating elsewhere in the world?
Oh, we have the biggest range of all in Europe, between 40 and sometimes 120 euro per megawatt hour. That depends very much on the circumstances of the system. But we cannot generalize that a lot, but we know that Mexico is very cost competitive. I think you have the advantages in these irradiation. I'm really jealous if I hear the 1,800 you are talking about as a nice, area for concentrating, because we are talking about 800 to 900 in Germany, and you can save a lot on the parabolics. As you have not so valuable mirrors, and even some of them do in Mexico work without vacuization in the pipes, so that you have a non-evacuated heat receiver, which brings costs down. So Mexico, they are sometimes at 15 or something euro per megawatt hour. So you can save on this regard, but they only do temperatures at the 120-degree range, So we don't see so many high temperature systems yet in Mexico. I think if you go above 150, you have to do evacuated receivers.
we are talking about, LCOE on per kilowatts, not megawatts. So
yeah,
need to take some zeros off there.
Yeah. Thank you, Peter.
We have a question for François. François, it's Trevor Lee asked the question. The new heat diagram showed all heat passing through the storage tank. The question is there no advantage to being able to pass the heat directly to the end use when the storage temperature has fallen significantly?
Yeah, absolutely. The diagram is well, not very accurate, and there is of course a bypass during the day when the heat can be used directly. That being said, most of the time it goes through the storage for regulation, and because of having this solar production, and it's so specific to this technology, so related to the sun radiation. So in summer at 12, you have a large overproduction compared to the usage, and you always need to buffer what's produced and what's been used. But well, in practical, you have a bypass of the storages.
Thank you. And Francois, I see you answered a question there in the Q&A there from Mark Pickering, wondering about the 25-year contract, and that's when we were doing some research on this over the last 12 months. That seems to be quite a stumbling block. I think you've got the answer there, saying this is you've done some ways to give them certainty there.
Yeah, and I think it's one of the pain points of our project with solar thermal. When you ask an industrial site to commit for the next 20, 15, 20, 25 years, it's very difficult for many reasons. And it's always a bit specific. In that case, we were lucky enough for the site to be in a, let's say, healthy and strong position. They were investing in a new processing line with a 20, I don't have the exact number, but it was about 25 years lifetime or 30 years lifetime as well. So it was the perfect match for them as they were doing this investment decision on their process. They were comfortable enough to commit of purchasing the heat for the same duration. And from our point of view as an investor and from the other investor behind newheat, it was a strong signal enough for us to be reinsured. In addition, for the site to be part of a big group, major company that was backing up the contract in case the case is the site's going to close down. That's the worst issue we need to think of in when designing the contract.
Got it. Thanks very much for that, Francois. Just so we got one final question there. I think we have time just one more from Brad Woolner about the list of suppliers. Brad, we've got a few ourselves. We'll send that through to you on the suppliers in Australia there for sure. And the likes of newheat is certainly here to support solar thermal projects as well. So we'll get something through to you there, Brad. Good. Mark, how are we doing? I think we're just about out of time.
You're muted, Mark.
One final question here from Nuri. What is the landed cost in Australian dollars per megawatt hour thermal installed in Australia for newheat technology? That's probably
just so we don't have technology. We pick the technology where we can, and those we answer with a different angle, but we pick technology where we can beat the gas prices. And the answer is for solar thermal. We find projects mostly as a heat as a service with flat plate collectors where we can beat the $20 per gigajoule mark, which is what we found to be the average price paid by industrial sites for their gas prices. So the answer is we find technologies where we can beat that mark of $20 per gigajoule.
Done. Thank you so much for that, Francois. And just to wrap up now, I'd like to say thank you to our fabulous panel and speakers here today. Thank you to Bärbel, to Keith, Francois, Ken, and Paul for joining us. Great to bring solar thermal up higher in the priorities and get people looking at this closer. Well done. Congratulations to Mars for their project. They're moving ahead, and congratulations to Impacts as well on that project for Charles Sturt University. And so that leaves us to wrap up for this webinar. Just to remind you, next week we have a member event next Tuesday afternoon in Melbourne. We're bringing out the global expert in high temperature heat pumps. And when we say high temperature, that's sort of that 100 to 160 degree range. Dr. Corden Arpagaus will be joining us for a presentation there. He's actually coming out for 2 weeks for A2EP, and so we're doing a series of presentations and meetings with the end users, and then to wrap it up, we're going to have some meetings in Canberra and with government there to let them know the findings of what's possible with R&D and opportunities for high temperature heat pumps in Australia. So that's over the next couple of weeks. We also, after Corden's presentation next Tuesday, a member mixer, and please go to our website to register for that one. Recent highlights, in case you missed it, we're coming off the back of this Australian Renewable Heat Conference. For members, you can reach out and get a highlights package for that, and the presentations, they're all available there for you. Just let us know if you need those. But we had a fantastic event. Great to see 200 people all talking about real projects and ways to make them happen and how to do things. So this was fantastic. And finally, if you want more A2EP, go to LinkedIn and just follow us there. You'll get the latest news of what we're up to and insights on grants and projects and things going ahead. So once again, thank you to our panel and presenters today. Thank you for joining us for this webinar, and we look forward to seeing you next time. All the best for the afternoon. Goodbye.